Section 10.3, the gas laws. Experiments with a large number of gases reveal that 4 variables are needed to define the physical condition or state of gas: temperature, pressure, volume, and the amount of gas, which is usually expressed as the number of moles. The equation that expresses the relationship among temperature, pressure, volume, and moles are known as the gas laws. Because volume is easily measured, the first gas laws to be studied express the effect on the variables on volume, with the remaining 2 variables held constant. The pressure-volume relationship, Boyles Law. If the pressure of a balloon is decreased, the balloon expands. That's why weather balloons expand when they rise to the atmosphere. Conversely, when a volume of gas is compressed, the pressure of the gas increases. British chemist Robert Boyle first investigated the relationship between the pressure of a gas and its volume. To perform the gas experiments, Boyle had a J-shaped tube shown like in figure 10.6. In the tube on the left, a quantity of gas was trapped above the column of mercury. Boyle changed the pressure on the gas by adding mercury to the tube. He found that the volume of gas decreased as the pressure increased. For example, doubling the pressure caused the gas volume to decrease to half its original value. Boyle's law, which summarizes these observations, states that the volume of a fixed quantity of gas maintained at constant pressure is inversely proportional to the pressure. When 2 measurements are inversely proportional, one gets smaller as the other gets larger. Boyle's law can be expressed mathematically as volume equals a constant times 1 over the pressure, or the product of pressure volume is equal to a constant. The value of a constant depends on the pressure and the amount of gas in the sample. The graph of volume versus pressure in figure 10.7 shows a type of curve obtained from a given quantity of gas at a fixed temperature. A linear relationship is obtained when volume is plotted versus 1 over the pressure. Figure 10.6, an illustration of Boyle's experiment relating pressure and volume. In the volume of the gas trapped in the J tube is 60 milliliters. When the gas is at pressure at 760 torr, when additional mercury is added, as shown in B, the trapped air is compressed. The volume is 30 milliliters and the total pressure is 1,520 torr, corresponding to atmospheric pressure plus the pressure exerted by the 760 millimeter column of mercury. Figure 10.7, graphs based on Boyle's law. Simple though it was, Boyle's law occupies a special place in the history of science. Boyle was the first to carry out a series of experiments in which one variable was systematically changed to determine the effects on another variable. The data from the experiments were then employed to establish an empirical relationship, or a law. We apply Boyle's law every time we breathe. The rib cage, which expands and contracts, and the diaphragm, a muscle beneath the lungs, govern the volume of the lungs. Inhalation occurs when the rib cage expands and the diaphragm moves downward. Both of these actions increase the volume of the lungs, thus decreasing the gas pressure inside the lungs. The atmospheric pressure then forces air into the lungs until the pressure in the lungs equals atmospheric pressure. Exhalation reverses the process. The rib cage contracts, the diaphragm moves up, both of which decrease the volume of the lungs. Air is forced out of the lungs by the resulting increase in pressure. The temperature-volume relationship, Charles's law. Hot air balloons rise because air expands as it's heated. The warm air in the balloon is less dense than the surrounding cool air at the same pressure. This difference in density causes the balloon to ascend. Conversely, a balloon will shrink when the gas is cooled, as seen in figure 10.8. The relationship between gas and volume and pressure was discovered in 1787 by the French scientist Jacques Charles. Charles found that the volume of a fixed quantity of gas at constant pressure increases linearly with pressure. Some typical data are shown in figure 10.9. Notice that the extrapolated or extended line passes through negative 273 Celsius. Note also that the gas is predicted to have 0 volume at this temperature. This condition is never realized, however, because all gases liquefy or solidify before reaching this temperature. In 1848, William Thomson, a British physicist whose title was Lord Kelvin, proposed an absolute temperature scale now known as the Kelvin scale. On this scale, 0 Kelvin, which is called absolute zero, equals negative 273.15 Celsius. In terms of the Kelvin scale, Charles's law can be stated as follows. The volume of a fixed amount of gas maintained at a constant pressure is directly proportional to its absolute temperature. Thus, doubling the absolute temperature, say from 200 Kelvin to 400 Kelvin, causes the gas volume to double. Mathematically, Charles's law takes the following form. Volume equals a constant times temperature, or volume divided by temperature is equal to a constant. The value of a constant depends on the pressure and amount of gas. Figure 10.9. Graph based on Charles's law. At constant pressure, the volume of enclosed gas increases as the pressure increases. The dashed line is the extrapolation of temperatures in which the substance is no longer a gas. Figure 10.8, an illustration of the effects of temperature on volume. As liquid nitrogen at 196 Celsius is poured over a balloon, the gas in the balloon is cooled and its volume decreases. The quantity-volume relationship, Avogadro's law. As we add gas to the balloon expands. The volume of a gas is affected by pressure, temperature, and the amount of gas. The relationship between quantity of gas and its volume follows from the work of Joseph Louis Gay-Lussac and Amedeo Avogadro. Gay-Lussac is one of those extraordinary figures in the history of science who would truly be called an adventurer. He was interested in lighter-than-air balloons, and in 1804 he made an ascent 23,000 feet, an exploit that held the altitude record for several decades. To better control lighter-than-air balloons, Gay-Lussac carried out several experiments on the properties of gases. In 1808 he observed the law of combining volumes. At a given pressure and temperature, the volumes of gases that react with one another are the ratio of small whole numbers. For example, 2 volumes of hydrogen gas react with 1 volume of oxygen gas to form 2 volumes of water vapor, as shown in Figure 10.10. Figure 10.10, the law of combining volumes. Gay-Lussac's experimental observation of combining volumes is shown together with Avogadro's explanation of the phenomenon. 2 volumes of hydrogen and 1 volume of oxygen yield 2 volumes of water vapor. 3 years later, Amedeo Avogadro interpreted Gay-Lussac's observation by proposing what is now known as Avogadro's Hypothesis. Equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. For example, experiments show that 22.4 liters of any gas at 0 Celsius in 1 atmosphere contain 6.02 times 10 to the 23rd gas molecules, that is, 1 mole, as depicted in Figure 10.11. Avogadro's law follows from Avogadro's hypothesis. The volume of a gas maintained at constant pressure and temperature and pressure is directly proportional to the number of moles of the gas. That is, the volume of the gas is equal to the constant times the number of moles. Thus, doubling the number of moles of gas will cause the volume to double if temperature and pressure remain constant.